For this problem, we're being asked to find the absolute extrema on a closed interval. So in this class, when you're asked to find absolute extrema, it's always going to include a given closed interval. And we're given the closed interval -3 to 1. So it includes -3 and 1. So absolute extrema means the points in this function in this interval where you have the very highest value and the very lowest value, and there will always be one. With the extreme value theorem telling us that any continuous function, that a function that's continuous on a closed interval, will have a highest value and a lowest value. This is a continuous function. It's a polynomial. There may be other functions that you'll see, but they'll be continuous if you're asked to find extrema on a closed interval here. Okay, so what we're going to do is we have some kind of function. I don't know what it looks like, but we're going to look for a very highest value and a very lowest value wherever they occur. And sometimes it occurs in more than one place. So what we're going to do is we're going to test points on this in this function, and they're going to be either the endpoints, that's where it could happen at an endpoint, or at critical points. So remember, a critical point are points where the derivative of a function is either 0 or undefined. With a polynomial, again, we don't have to worry about undefined, but we're going to look for the places where the derivative is 0. So we're going to find the derivative of this function, 2x plus 4. And you see that there's no value of x that'll make this undefined. We're going to set it equal to 0 and solve and see what value of x will make this 0. Subtract 4, divide by 2, so we have x equals -2. That's a critical point. I don't know that it's an extrema yet. It could be a local extrema, but or an absolute extrema. Right now, we are looking for absolute extrema. So I'm going to test this point and the endpoints, -3 and 1, in the function itself, because I want to know what the highest and lowest values are. So f of -3, f of -2, and f of 1. By the way, you should check to make sure that your critical point is within this interval, because if the only critical point that you find is outside the interval, you only have the endpoints. Okay, in this case, -2 is in our interval, and I'm testing the endpoints, -3 and 1, and I'm testing the critical point. So in this case, I want the values. I want to know exactly what the values are, because one's going to be the highest, one's going to be the lowest, or more than one place. So this equals -3 squared plus 4 times -3 plus 4, which equals 9 minus 12, which is -3 plus 4, which is 1. -2, so we have -2 squared plus 4 times -2 plus 4. -2 squared is 4. -8 is -4 plus 4 is 0. And the last one is 1. So 1 squared plus 4 times 1 plus 4 equals 1 plus 4 is 5 plus 4 is 9. So there are 3 values that we found at the endpoints and at the critical point. This value here is the highest value. This value here is the lowest value. So this is the absolute maximum. And that's all I'm asking you to find in the test. Just find what value is the absolute maximum. You can see that it occurs at 1, so you can say more about it. But if you write it in this kind of way, where it's very clear what it is, what the maximum is, where how you tested it, that it was tested in the function, and what points you tested, you're going to be fine. The lowest value is 0, so this is our absolute minimum value, and you're done with this problem. In this problem, we are given a function and we're asked to analyze it. Analyze the following function. And you're going to, on the exam, you're going to be given specific questions, leading questions here. So the first thing you're going to be asked to do is to find the critical numbers. Remember, the critical numbers are where the derivative of a function is either 0 or undefined. And again, we're working with a polynomial, so we're not going to have any places where anything is undefined. So we need to find the values where the first derivative is equal to 0. So we find the derivative here, which is 3x squared minus 10x plus 7. And we set this equal to 0, and we want to solve this equation. I'm going to look to see if I can factor this thing. So 3 times 7 is 21. I need 2 numbers that multiply to 21 and add up to -10, so they would have to both be negative, so they would multiply to a positive number, and they would add up to a negative number. Here we go, -3 times -7 multiplied gives us 21, positive 21, and add together they give us -10. And so I'm going to use that to factor these. This is called factoring by grouping. 3x squared minus 3x minus 7x plus 7. And I'm going to keep writing this equation here as I factor this on the left. I'm going to group these. 3x squared minus 3x plus -7x plus 7 equals 0. I'm going to factor out the greatest common factor, 3x, leaving me with x minus 1. Here I'm going to factor out a -7, so it's going to be -7 times x minus 1 equals 0. And of course, x minus 1 is a common factor, so we have x minus 1 times 3x minus 7 equals 0. And we set each one of these equal to 0, so x equals 1 and x equals 7/3 are our critical numbers. And we're done with this part. So remember that the critical numbers here are the only places where we can have extrema. They're also the only places where a function can go from increasing to decreasing and from decreasing to increasing. So the next thing we're going to be asked here is to identify the open intervals upon which the function is increasing and decreasing. So intervals increasing and decreasing. And they're going to be broken up by these. These critical numbers are the only places that could happen. And so we have 1 and 7/3. And we use these critical numbers to break up the interval upon which that this function is defined, which is all numbers from -infinity to positive infinity. If there are two critical numbers, it's going to break them up into 3 intervals. So these intervals are going to be -infinity to 1, from 1 to 7/3, and from 7/3 to infinity. So we're figuring out whether this function, the original function, is increasing or decreasing on these 3 intervals. So to do that, as we discussed in the first problem we did, or the second problem we did, this is going to happen. We can determine whether this is increasing or decreasing based on whether the derivative is positive or negative. So I pick a test point in this interval. Any point will do in this interval, because they're all going to be either increasing or decreasing, because it can only change at a critical number, so they've all got to be the same. So I'm going to pick easy test points, and I'm going to test those points in the derivative. I want to know whether the derivative is positive or negative. So the derivative evaluated at, let's say, 0. That's the easiest point in this interval here. That's a nice interval. And I'm going to test the first derivative at, let's say, 2. And I'm going to test the third interval here at 3. And if I got this right, each one of these test points is in the interval. And I'm going to strongly advise you on the test to set it up exactly this way, so it's very clear to me how you're testing, what intervals you're testing, where you're testing them in, that you're testing them in the first derivative, and so on. It'll be very clear. And it's just a good idea to just do it the way I'm doing it now. If you do it another way, that's fine, but it has to be clear, and it has to be all your conclusions have to be clearly identified. Okay, so again, I want to know whether this is positive or negative. I don't care about the exact value. I just want to know whether it's positive or negative. One of the easiest ways to do this, with 0, it's very easy to plug in. So we plug in 0 into our derivative. Here's our derivative, right? 3x squared minus 10x plus 7. So plugging in 0 in the x's gives us 7, positive 7. So I know that this is greater than 0 on this interval. And when x is 2, it's a little easier for me to go to this, which is the factored version. Be careful that you haven't lost any negatives up here. This is a factored version of this, and I plug in 2. And I just want to know if this is negative or positive. So if x is 2, 2 minus 1, that's positive 1. If this is 2, we have 6 minus 7, which is negative. Positive times a negative is a negative. So this is less than 0 or negative in this interval. And finally, with the number 3, I plug it again into this factored version of the derivative. 3 minus 1 is positive. 3 times 3 is 9 minus 7 is positive. Positive times positive is positive. So this is greater than 0 here. Okay, so the question was to determine which intervals the function is increasing or decreasing, and that, of course, depends on the derivative, whether it's positive or negative. So in this interval, this derivative is positive, so the function is increasing. In this interval, 1 to 7/3, the derivative is negative, so this is decreasing, and this is positive, so it's increasing. So that answers that question. The next thing you're going to be asked is to identify all relative extrema, and finding the critical numbers and evaluating the intervals where they're changing and where they're going increasing and decreasing is, in effect, the first derivative test. And so you only have one thing left to do. You have your critical numbers. That's where we have possible extrema, a minima or maxima, and we just have to know what's happening to the left and the right of them. So in this case, it can be helpful to draw just a little diagram. If the function is increasing on the left, decreasing on the right, we have our critical point happening at the top of the hill, so we have a maximum here. And here, when we have, here's our critical point of 7/3, and on the left it's decreasing, on the right it's increasing, we have a local minimum. Okay? If these weren't changing from positive to negative or negative to positive, then we wouldn't have an extrema. It just wouldn't be an extrema. But this is our answer. This is sufficient for me to tell me where we have local extrema. If you write maximum and everything is very clearly written, I can see your points. It may be safer to write maximum at x equals 1 and minimum at x equals 7/3. I'm not asking you to find the values there, just where it's happening. Okay, and that's all you have to do in that part. So the next thing you're going to be asked to do with this same function, and I copied the function and its derivative here, is to find possible points of inflection. And then after that, we're going to be asked to find open intervals on which the function is concave up and concave down, and to confirm that we have points of inflection. So points of inflection are where a function changes concavity from concave up to concave down. So we need to look at the second derivative, because we have concavity when the second derivative is less than 0. When it's negative, that means we have concave down. Our function is concave down. When the second derivative is greater than 0, it's concave up. And to remind you why this is, remember that the second derivative is talking about how the first derivative is changing. The first derivative is the slope of the tangent line at any point on a function. And if draw a bunch of tangent lines on a function, let's say we have a function that looks like this. If you draw, as we're going from left to right, the tangent lines, so the slope of the tangent lines is indicated by the first derivative. The second derivative is talking about how these are changing, how the slopes are changing. Well, they're all positive in this case. It doesn't matter, it can be negative, but they're all getting lower. They're going down. Okay, so the slopes of these tangent lines are getting smaller, and so that we have then a negative second derivative. It's getting smaller, therefore it's concave down. Okay? So let's look at. So we're now finding the possible points of inflection. And so I'll just do one more little drawing. So a point of inflection would be where it then changes from concave down to concave up, and that would be somewhere around here. And that's the only place that a function can change concavity, is that we call that a point of inflection. That's going to happen at places where the second derivative is equal to 0. So we find the second derivative, which is just the derivative of the first derivative. So we have 6x minus 10. We set that equal to 0, and we add 10, so divide by 6, and we have x equals 5/3. There is our possible point of inflection. it's not necessarily a point of inflection, just like critical points. Critical points point out places where we can have an extrema, but it doesn't necessarily mean we have an extrema. It's only, this is the place where it can happen. It's not a point of inflection if it doesn't change concavity at that point, but we have the point where we can now test. And the next thing we're being asked to do is identify all open intervals on which the function is concave up and concave down. And because it can only change at this point, at this possible point of inflection, that's how I split up my interval. -infinity to 5/3 and 5/3 to infinity. And I pick its S point, and again, I now want to know what the second derivative is doing. Is a second derivative negative or positive, and therefore concave down or concave up? So I'm going to pick a value, an easy value here. The easiest value, of course, here would be 0. So I want to know what the second derivative is doing at a test point in this interval. And I want to know what the second derivative is doing at another test point, let's say 2, in this interval. And again, I don't care about the exact value. I just want to know positive or negative. So here, keep in mind, here is our second derivative. And so plugging 0 in, I have -10, so it's less than 0. And here, plugging in a 2, 2 times 6 is 12, minus 10, that's positive, greater than 0. And so I can conclude that in this interval here, the second derivative being negative means that this is concave down. And because the second derivative in this interval is greater than 0, we can say that in this interval, we have that the function is concave up. And I've answered that question. The final question that you'll be asked for this kind of analysis is to identify the point of inflection. And a lot of people get confused because they thought they already did that. This is a possible point of inflection. It only is surely a point of inflection when we can say that concavity is changing from down to up, or from up to down on either side. Then it's a point of inflection. So I would say that the point of inflection does occur at x equals 5/3, and we're done. In this problem here, we have an optimization problem. It says where line y equals 2 minus 3x closest to the point 1, 2. So let's see why this is an optimization problem. So generally, just to draw a picture for myself, just to give myself a visualization of what's going on here, we have a line y equals 2 minus 3x. That means we have a y-intercept of 2, and we have a slope of -3. So we have something that, I'm going to have trouble drawing this, something that vaguely looks like that. We're being asked, where is that line? At what point on this line is closest to the point 1, 2? So let's say, like somewhere up here. Okay, 1, 2. So this is our point 1, 2. I don't know if this is accurate. I'm just kind of estimating. Actually, it would be a little off. But in any case, this is generally what I'm asking. It doesn't even matter where your line is, just to give the idea of what's happening here. Well, here's our point, 1, 2, and there's some point on this line, not here, because you can see the distance between here and here would be too long. This would be, there's some shortest distance. In other words, if you look at it, it's basically where it drops to a right angle, but we're not dealing with angles here. We're dealing with, we're going to deal with distance. But there's some point here that's the closest. You can see, if you think about it, that this is the closest point. And we're going to call that point xy. And we have to identify the x and the y values of this point here, knowing that we want to get it closest to 1.2. The reason this is an optimization problem is because we want to find the shortest distance. We want to minimize the distance between this point, 1.1, 2, and this line. And we have this information here. We're told that at this point, x is 1, this point, y is 2, and we have this equation. What the secret here is to figure out an equation that relates all these things. Well, that would be our distance formula, the distance between one point and another point. We're given the 1 point, 1.1, 2, and we need to find the other point, x, y. But our distance formula is distance equals the square root of x1 minus x2 squared plus y1 minus y2 squared. You can figure that out any way you want, but it's basically if you think about it, the distance between the x values and the distance between the y values, and it's a Pythagorean theorem that's involved here. That's why it looks like this, okay? But this is how we figure this out. This is the distance formula. And the distance between these 2 points is what we're trying to minimize. So I'm going to approach this in a simple way, and I'm just going to ask you to find the minimum. I'm not asking you to find the endpoints and test those and to show whether it's a maximum or minimum. I just want you to find the critical points here, which is going to give us, in this case, our minimum. Or if you're asked for another problem with a maximum, I'm not asking you to go too far and to show everything. I just want you to find those points. So I'm going to minimize this equation here. So I'm going to fill in all these parts. So my distance equals the square root. Well, x1 we're gonna call that just x. So the distance between one point x, which is just x, minus the other x value, which is 1 squared, plus the distance between the y value here, which is just y, and the y value here, which is 2. So y minus 2 squared. Okay. So we have a formula here that relates distance to x and y, and we want to take the derivative here. But the thing is, right now I have x and y. Distances in terms of x and y. I want to have distance in terms of only one variable. So we need some other bit of information about these points, so I can get rid of one of these variables, so I can solve for one of them. And that, of course, is what we're given right here. We have that information. We have the relationship between x and y. It's given in the equation of the line. Y equals 2 minus 3x. We're going to use that to substitute that in for y. So instead of y, we're going to plug this value into y, because that's what y equals. And then we'll have everything in terms of x. We'll have the distance only in terms of x. So let me write that out again. Distance equals the square root of x minus 1 squared plus, and I'm going to put this in brackets like this because I'm going to use parentheses inside, but it's not that important. Instead of y, it's going to be 2 minus 3x minus 2. Okay. So I've just substituted 2 minus 3x for my y. There is my distance formula that is only in terms of x now. Okay. So this is the distance between these 2 points, 1, 2, and some point on the line xy, and we want to find that smallest distance because there are many points xy on this line, but only one of them is going to be the smallest, give us the smallest distance. Okay. So what I'm going to do here is simplify what's under here. So distance equals square root of, and I'm going to just expand this and combine like terms and all that. So x minus 1 squared is x squared minus 2x plus 1. And then in here we have, I'm going to do this in 2 steps, 2 minus 3x minus 2. So the 2's actually cancel out and we just have 3x squared. And so we finally have d equals, well, I shouldn't say finally, x squared minus 2x plus 1, and then plus 3x squared, which is 9x squared, right? 3 squared, x squared, and so on. And one more simplification under there, combining the like terms, 10x squared minus 2x plus 1. Okay? So there is the simplest form that I can find of the distance in terms of just x. And so now I can easily take the derivative of d with respect to x, only one variable, and I'm going to find the point at which that is equal to 0, which will give me in this case, my minimum. Okay, so it looks like it would be a little complicated to take the derivative of a square root function, but luckily we have a little bit of a trick here. This function underneath here, okay, inside the radical, the 10x squared minus 2x plus 1, I'm going to call that h of x. I'm just labeling it something. And I'm going to notice that in order to find the minimum distance, in other words, the square root of something that gives me the smallest amount, if I can find the minimum value of h of x, then that's enough. Whatever the x value is that gives me the smallest value under the radical, then that's going to be the smallest value I can find. So in other words, I don't have to deal with the radical. I can deal with just the parabola that's under here and find the value of x that provides me a minimum of that. Think about that. Okay, go back and try to think of what I mean by that. But I don't have to take the derivative of the square root of this parabola. I can just take the derivative of this of the parabola inside of it and figure out what that value is. And that's the same. It's going to be the same value that makes the distance the smallest. Okay, so let's take that function. I'm going to move up here, and we have h of x equals 10x squared minus 2x plus 1. And I'm going to find the derivative of that function, which is 20x minus 2. I'm going to set that equal to 0, and I'm going to solve. Adding 2 dividing by 20 gives me x equals 1/10. There is my x value. Okay, in other words, that is the point on this line that is going to give me, that is going to be the closest point to the point 1, 2. Okay? So in this case, again, I'm not asking you to prove as you would with an absolute absolute value function that the endpoints are, that there are other points. Just going to deal with this right here. I'm going to accept this answer that x is 1/10, and I do need to find the y value, the coordinate of the y coordinate here. So if I know what x is, I just go up here at y equals 2 minus 3x. That's how they relate, and I figure out what y is. So if x is 1/10, y equals 2 minus 3 times 1/10, or y equals 2 minus 3/10. I have to just add these together. So this is going to be the same thing. 2 times 10 is 20. 20 minus 3/10, or 17/10. That can't be simplified anymore. So my point is the point on the line y equals 2 minus 3x that is closest to the point 1, 2. I'm just going to double check, make sure that actually is what I was asking. 1, 2 is 1/10, 17/10. Okay. You don't necessarily have to write out this sentence, but it kind of helps to summarize what exactly you're finding. But I would want to know what this point is. That's the point on the line, and that is a point on that line, y equals 2 minus 3x, and that's the point that's absolutely closest to the point 1, 2, and that's it.